All right, everybody. What we're going to do is we're going to look at a few problems together. Good to see you guys. That is hypothetical because never mind. Never mind. Okay. Number one. So what we got was 7.3 here. We've got an Atwood's machine. So what we have is we have mass 1, and my problem is 1.15, and mass 2 is 3.05. All right. So they go up and over a pulley. No friction, pulley's massless. Woof. First question, what's the acceleration? And it's always the first thing you need to do. So do F net equals ma. Now this guy has a weight force, and this guy has a weight force. They're not working together, they're working against each other. So the F net is the weight of the 3 guy minus the weight of the 1 guy equals the addition of the masses. Okay, so there's where I'm starting. So 3.05 times 9.8 minus 1.15 times 9.8 equals sum of the masses, 4.2. Solve for A. I'm getting acceleration. Let's get a number. I'm going to type. I got to get a better calculator. All right, here we go. The 8 stopped working. Divided by 4.2. There we go. I get 4.43. So my acceleration is 4.43 meters per second squared. All right. Now we're going to use that because this next question is, what is the tension? What I do is I pick one of them. I'm just going to pick this guy. Why? Because I can. It doesn't matter which one you pick. So this guy here has a weight force going down and a tension going up. Notice how I drew the upwards one smaller because it's accelerating downwards. So the weight force is mass times gravity. I didn't write the number down. Tension, we don't know. We're solving for it. But what I can do for the individual, remember we're just looking at 1 now, I can do F net equals ma. So the mass is 3.05. The acceleration is 4.43. I can solve for my F net. I'm going to get that number real quick. 13.5. Well, if that's my F net, oh, my weight, let's get that guy in there. 29.89. Okay, so that is my weight force. Well, my F net is 13. Well, so that means my tension is 29.89 minus 13.5. It's smaller. So minus 13.5, 16.39. That's it.
Yo.
What's up? All right. Here we go. Sorry. This is how many times Lenberg was sarcastic at the staff meeting. All right, here we go. So what we got is an Atwood's machine. Mr. Sarcasm himself. Number 2 here. So the key to this is to find the acceleration is we look at the weight forces off of these. So this guy is 2.25 times 9.8. And this guy is 2.10 times 9.8. And so let's just get some numbers, okay? 2.25 times 9.8, 22. Okay, and the other one is 2.10 times 9.8, 20.5. Now, if you look, as it goes over this pulley, those arrows are in opposite directions. They're working against each other, okay? And so if I look at the F net of my system, F net equals ma, I have the larger one minus the smaller one, and then the mass is both of them together. So when I solve for A, I get a small acceleration, 0.34 meters per second squared. It's not much. All right, so now we're going to go into number 3. Where's my mouse? There it is. So number 3. So number 3 here, we've got a little bit different way. An ultra low friction pulley. Sweet. Got it. I have to find those somewhere. The 2 weights attached are accelerated at 5. It's at 5 meters per second squared. This is number 3. So let's think about this. So F net equals ma. Here's the problem. I know what one of the masses is, but I don't know the other one. I know the acceleration though. Ooh, we got that going for us. It's kind of backwards, right? F net is the weight force of this guy minus the weight force of the other guy. So remember how weight equals m times g? So I would do mass times gravity, mass times gravity. And just like we did on the other ones, right, you've got a tug of war. You've got one going one way, one going the other. Let me show you draw this just to reinforce that. So this guy feels a force and this guy feels a force. And since it's accelerating up, I know this one is bigger and this one is smaller. So I subtract, so the big one minus the little guy. Big guy minus the little guy. Okay, so now I've made a mess of everything. So now I'm second guessing a lot of things in life. We got 10.58. I'm just going to write it down. 10.58 minus 9.8 m. Now I'm going to distribute this out. So 5 times 1.08, get 5.4 plus 5m. What I'm going to do is I'm going to get all my m's on one side and all my numbers on the other. So I'm going to subtract off the 5.4, and then I'm going to add on the 9.8. Five plus 9.8, 14.8. Whoa, I need coffee. All right, and then 10.58 minus 5.4, 5.18. Divide that off, 0.35. This to me is it's a tough problem. Okay, so yeah, just wanted to share that one with you. Thanks for showing up. The next one we haven't even talked about. Okay, but we're gonna walk through the ideas to get you there. So let's look at our situation on number 4. Number 4, I have a system. I have multiple forces. I have this guy attached to this guy. What we need to do is to think through what are the forces. So let's start on this guy. This guy is 4.2 kilograms. So if I take 4.2 times 9.8, get 41.6. 41.16 newtons. Okay, that's the force there. Next up, this is mg sine of theta, pulling it down the ramp. So 4.5 times 9.8 times sine of 35. You get 25.3 newtons. Now visually, which way is it going to go? It's going to go this way. It's a larger force. So if I look at my system, F net equals ma. So my F net is 41.16 minus 25.3. How much mass is being accelerated? Both of them, 8.7. Solve for A. I'm not doing it. All right, number 5. Now we're going to get into friction. Now, this first one I have on here because it's all conceptual. So in this first guy, we've got a box, and it's getting pushed into the ground. If the angle between the horizontal force is increased, let's think about this. If I start with this angle, I've got a certain amount sideways and a certain amount down. What happens if I make it steeper? What happens? The sideways force gets smaller, and the downwards force gets bigger. Okay, so there's my ideas I'm going to work with. So in this problem, it says if the angle between it gets bigger, f of x gets smaller. If the angle between the horizontal force increases somewhat, does friction increase or decrease or remain the same? Now, The box is stationary, meaning the box has a velocity of 0, an acceleration of 0, and it ain't moving. So you have an F net of 0. So that means this forwards force equals that friction. So this is your static friction. Well, if you made that forwards force smaller and it still doesn't move, what does that mean about your static friction? It's going to be the same as that forwards force, but since the forwards force got smaller, it gets smaller too. I'll move me over there. If the angle increases, does the normal force change? Well, let's look at this. Before you only put, I'm going to do green for normal force conversation. I shoved in a little bit, but now I'm pushing into the ground more. Well, originally my normal force was here, but if I push into the ground more, I'm going to need more normal force to counteract that. A lot of times we talk about pulling, how the normal force gets smaller. Well, if you push, you're pushing into the ground, it gets bigger. So normal force gets bigger. If the angle between gets bigger, the max static friction. Now we're talking. So static friction, okay, here's what's important. Static friction, if it's not moving, it just equals whatever it needs to be. But it goes up to a maximum value of mu times normal. So we say static friction is less than or equal to mu times normal. So it builds up to a maximum value. It builds up to this breaking point. So in this problem, if you push more into the ground, you get a bigger normal force. You get a bigger normal force, you get a bigger maximum static friction, a bigger breaking point when it's going to break off. 6. All right, 6 I have on here because it's kind of a building block. Bedroom bureau. So some of you are Googling what that is, also known as a dresser. Okay, so we've got a bureau with a mass of 37. Ooh, that's good. 37 kilograms. Clothing rests on the floor. Coefficient of static friction is 0.30. How much force does it take to get moving? Okay, so there's my question. What does it take to get it moving? Well, I don't know. So force static is going to equal, the maximum value is going to equal mu times the normal force. It's on flat ground. So the normal force is going to equal the weight force. Here's you pushing, here's the static friction. Those are going to be equal until it breaks free, okay? But notice how your normal force equals your weight force. So this max static friction is the coefficient times the gravitational weight. 37 times 9.8, because they're equal in this case. So the static friction is a number, okay? Now we remove 13 kilograms. This number is going to get smaller. We're going to have a smaller mass to use. All right, number 7. I found this problem. I had to give it to you guys. It was too good to pass up. What we've got is Henry Sinkoski of Philadelphia spent himself from rafters by gripping the rafter with the thumb of each hand on each side and the fingers on the other side. He's got a mass. Oh, that's good to know. Thanks. So he has a mass of 79 kilograms. Okay. So let's just start there. He's got a weight force of 79 times 9.8. 774 newtons. So in other words, his little fingers have to be able to do that. Coefficient of static friction. Static friction is 0.67. The coefficient of static friction between the hands and the rafters is 0.67. What is the least amount of normal force he has to apply? This is kind of a weird one, okay? He literally grabbed onto the rafters and moved. This is an amazing feat. So we have a weight force, okay? And this is where it gets confusing. What's the force that keeps Henry from falling? It's friction. Watch this. If he doesn't squeeze hard enough, does he start to fall? Okay, this is kind of a weird situation. His hands are part of his body. So as he pushes on the rafters push back with a normal force from both sides. So this is where it gets interesting. Let's just assume these are going to be the same off his hands, right? I don't even think we have to assume that. They have to be. So this is where it gets weird, right? So static coefficient. Jeez, I can't believe. I'm sorry, guys. It's 0.67. So friction is mu times normal. Okay. But what we're going to do is we're going to get some information here. So mu 0.67. Normal force. We'll just solve for n, right? We're just going to solve for the total normal force, but just know that it's on both sides. So we're going to try both of those numbers and see which one sticks. And so static friction. Now here's where we got to put our little thinking caps on. That friction force upwards has to equal that weight force downwards, or else he's going to start sliding. Okay, he's got to have enough friction to support him. So if he's got 774 weight force, he's got to have 774 friction, or else he's going to fall off. Okay, so that means my friction force equals mg. But since we know what it is, we're just going to put it there. So we got 774 equals 0.67 times normal force. This is the normal force he needs. 1,155 newtons. That's total. So how much does he have to have on each hand? He would have to have half of that. But I don't know. I can't even plug in answers. Right? But it's going to be one of those two. Either they want the total or they want to know what each of them is. So there you go. If he can't squeeze that much, doesn't matter. He falls. All right, we got ourselves a pickup truck. Here, oh, pick 'em up truck. Oh, sorry, a pickup game of dorm shuffleboard. First up, I love these types of questions. This is like somebody having too much fun. Students crazed by final exams use a broom to propel a calculus book along the dorm hallway. If the 3.5 kilograms, mass 3.5. Okay, I'm just writing down information. Travels a distance of 0.74 meters. By the horizontal 20 newtons of the force. All right, okay. And then has a speed of, final speed is 1.52. What is the coefficient of kinetic friction between them and the floor? Whoo! We've got ourselves a problem, people. Literally, we have a problem. So what we have is, let's start by finding my pen. There it is. So let's start with what we know. Person pushes with 20 newtons. There's a normal force and a weight force. This is a picture of just the 3.5 kilogram mass. There's also going to be friction. Okay. Now, weight force is mg. So 3.5 times 9.8. We just get a number. So 3.5 times 9.8. 34.3. Well, that's the weight force. Since I'm on flat ground and there's nothing weird going on, that's my normal force also. Okay. Now, they give us information about distance and velocity right off the bat. We need to go this route. Starts from rest, ends up at 1.52. I think your problem would be different. Acceleration, I don't know. Delta x, it goes 0.74 meters. Time, I'm going to tell you right now, we don't care. Okay. I'm going to say we need to know acceleration. Here's why. We're dealing with forces. If I can solve for acceleration, then we can get forces. So I'm going to use VF squared equals V initial squared plus 2A delta x. So VF squared 1.52 squared equals 0 squared plus 2A 0.74. Solve for A. I'm just going to get a number, get a value, 1.52 squared divided by 2 divided by 0.74. 1.56. Okay. Now, we're going to use that. We're going to come over here. We're going to say, all right, I know The acceleration is 1.56. They gave me information about motion, so I have my acceleration. Okay. If I do F net equals ma, ready? I know my mass, 3.5. I know acceleration. Ooh, we're getting somewhere. I'm going to write a setup for what the F net is from my picture. It's 20 minus the friction. Okay. Now, 20 minus friction, which is mu times normal. I'm going to get 5.46. Okay. Now, this problem wants me to find mu. I have one thing in my way, normal force. So 20 minus mu times normal, 34.3 equals 5.46. Solve that out, I get a number from mu. Okay, move the 20 over, divide by 34. Do you see the complexity of the problem? These are not like, oh, that's just one step and I'm done. F equals ma. Nah, instead you got to go, okay, they gave me stuff about motion, get acceleration. I need to draw my force body diagram. I need to set something up that relates forces and acceleration. So my F net equals ma statement. All right, let's get into number 9. Number 9 starts dealing with 9 and 10. I looked at kind of the records of how long these ones take. These ones are a little bit tougher. So look at number 9. We got number 9. We got ourselves a box, and we're going to push it into the ground. We pushed it with 19 newtons, minus 25 degrees, and the box is 2.6. So if I do 2.6 times 9.8, 25.5. Okay, so I've got some basic information. Coefficient of sliding friction is 0.25. Okay, so we've got our information started. Okay, calculate the magnitude of the frictional force in the block from the floor. I don't know. Well, let's start there. Part A. Force of friction is mu times normal. Well, look at this. They gave me mu. That's good, right? It's moving. I don't know my normal force. Right? If it was just on flat ground, I wasn't pushing it, it would be 25.5. This is number 9. It'd be 25.5. Problem is you're pushing into the ground. So let's find out how much you're pushing into the ground. So this will be 19 cosine of 25. This will be 19 sine of 25. Let's get these two values. Cosine of 25, 17.2. Or 19 sine of 25. Just 8, rounds to 8. It's cool. So if I look here, I'm going to use yellow just so we don't cross everything else. Here's my weight force going down. Here's part of my push going down. I got 25.5 going down, and I got 8 going down. Well, how much has to be going up as my normal force? It has to be those guys together. It has to counteract them. Is that 33.5? I got to have 33.5 as my normal. My normal force got bigger by pushing into the ground. So I now have a frictional force. So I've got 33.5 times 0.25. I have friction. It's 8.37. So I'm going to go into my picture. I'm going to draw that. Force of friction is 8.37. The last question is, what's the acceleration? Okay. So let's just, okay, acceleration, F net equals ma, right? I know what my mass is. Do I? 2.6. Okay. I don't know what my acceleration is, but F net. Okay. This block's going to be going sideways. Well, how much force is going forward? 17.2. How much force is going backwards? 8.37. That's it. It's all for acceleration. There you go. All right. Let's get this out of here. All right. Let's do number 10. 10 and 11. Here we go. I think if I didn't say it, I think 10 and 11 are going to be extra credit. You can do them, but just letting you know. Loaded penguin, sled wane. So I have a weight force of 76. okay? 20 degrees, okay, to the horizontal. Between the sled and the plane, the coefficient of static friction is 0.22, and kinetic friction is 0.16. All right. What's the minimum magnitude of the force parallel to the plane that will prevent the sled from slipping down the plane? What is the minimum magnitude of the force to keep it from slipping down the plane? Okay? If it's about to slip down, right, no matter what, we got mg sine of theta. Let's just solve for that. So we got 76 is mg sine of 20. So let's do 76 sine of 20. It's 26. So in all these problems, I'm going to have 26 pulling down the ramp. I got 26 newtons pulling down the ramp. So how much do I have to have going up the ramp? I got to have 26. So the wrong answer is 26. Because if there's no friction, that is a great answer. You got to have 26 newtons up the ramp. Perfect. But here's the catch. Yes, you have to apply a force, but you have something helping you. Do you have a little bit of friction helping you? We need to find out what that friction is. This is static. It's not moving. Okay. The biggest that static friction will be is 0.22 times normal force, which is mg cosine of theta. The normal force on a ramp is mg cosine theta. So 22, my mg is 76. Cosine of 20. Let's just get a value. So 0.22 times 76 cosine 20, 15.7. So the maximum the static friction will be is 15.7. So look at this. That means you don't have to push as hard. So how much do you have to push? The rest. So 26 minus 15.7. You only have to push with 10.3 newtons. That's it. That's all you have to do. Just that little bit, and it'll stay put. What is the minimum magnitude F that will start the sled moving up the plane? Hold on. This is going to get weird. So let's think about this. If I start to push this thing up the plane, this is where it gets a little bit interesting. If I start pushing it harder to get it going up the plane, I got mg sine of theta going down the ramp. Okay, that has not changed. That's 26. But if I try to push it up the ramp, is the surface now going to resist me? And the static friction is going to be going down. That, to me, is the weird part of this question. This is why I put it on there. Not to stump you. That's not what I'm doing. I'm trying to open your eyes and go, whoa. If I push one way and I'm trying to get it to move that way, the static friction will oppose that. In that direction. Well, what's the biggest it'll be? 15.7. We did all this work. So 26 going down, 15.7 going down, you would have to push more than, I can't do mental math. Please don't judge me, 41.7. I just added these up. If I wanted to go up the ramp, I got to push more than 41.7 to get it going up the ramp. Okay. Well, that was part A and B. What will it take to move the block up the ramp at a constant velocity? Ah, come on, Schmear. All right, so let's take a step back. We're gonna make this blue. If I want to have it go up the ramp at constant velocity, where does it go? There it is. Now, this is subtle. If I want to go up the ramp at constant velocity, I still have mg sine of theta going down the ramp. I still have friction going down the ramp, and I still have my push going up the ramp. But once it's moving, it's easier. So this is not static friction. This is now kinetic friction. Oh, Schmear, right? So mu times normal. So we got 0.16 times mg cosine theta, which is 0.16 times 76 times cosine of 20, 11.4. So now, yes, there's 26 going down the ramp. Yes, I still have to oppose that. Kinetic friction is smaller. It's a little bit easier. So I only have to push with 37.4 newtons now, not as much. All right. All right, last one, guys. This will be a good one. Let's do this one, and we will call it a day. All right. Block of mass MT. MT is on the top, MB is on the bottom. Block of the bottom is 5.5. To cause the top block to slip on the bottom one, well, the bottom one is held fixed. The horizontal force of 21 must be applied to the top block. Okay, so we're going to use that information. If you want to get the top block to move, okay, static friction for the top block is 21. I got to push it with 21 to get it moving. Okay. The assembly blocks is now placed on a horizontal frictionless table. So now the blocks are here on a frictionless table. So there's no friction down here, but there is friction up here. Yes, there is friction between the blocks. Okay. Find the magnitude of the maximum horizontal force that can be applied to the lower blocks so the top blocks will move together. Well, watch this. The biggest that this friction force can be to keep it there is 21. That's the biggest, right? That, if I pull with 21, it just starts to break free. Well, the top block has a mass of 4 kilograms. Okay? That friction force is the force that's going to get the top block moving. So if I look at the top block, if I do F net equals MA, his mass is 4. His F net is going to be 21. So his acceleration is going to be 5.25. If I accelerate more than that, it slides off. If I accelerate less than that, it stays put because that static friction can be smaller too. So that's my acceleration. Oh, we just accidentally answered part B, 5.25. Okay. Find the magnitude of the maximum horizontal force that can be applied to the lower block. So now let's think about this. If we applied a force here, how big could that be? Well, this force is going to accelerate the whole system. So this force that we apply is going to be that is going to be the F net because as it applies a friction force to the bottom one, these will be third law force pairs and cancel out. But as you apply that force, that's going to be your F net. So if I do F net equals MA, F net, my applied force for the system, equals the two masses put together, which is 9.5, and my acceleration is 5.25. So my force applied is 9.5 times 5.25. I can pull with 49.87. Now here's the key. When you pull 49.87, you move both of them. You accelerate both of them. That top one only needs 21 to accelerate it. And so it's a little bit easier move. Again, 11, tough one. If you're like, I got to get a 5 on this AP exam, keep playing with those. If you're like, man, I'm just trying to understand friction, make sure you can do the ones before number 9, right? Those are the ones I want to make sure you can do, especially just pulling stuff on the ground. So there you go. 11 is starting to combine systems and friction. We're going to keep practicing in the class. So there you go, guys. Stay in school. Talk to you guys later. Thanks for coming. All right, guys.